Good evening, I am Mr. S. Thank you for joining me. Very recently I presented a video on partial fractions decomposition, an essential technique especially when you want to integrate rational functions where the polynomial in the denominator has a higher order exponent than that in the numerator. This is ideal for this technique, partial fractions decomposition. In this video, let's take that message from that previous video one step further and take two questions all the way through to completion. We have this rational function and we need to integrate it. Let's decompose it first. We're looking at 2x plus 3, and you know we have to factor out the denominator because that will determine the number of partial fractions that will generate. You have x plus 1, x plus 3. You see that, right? If you were to open this up, multiply it, and you'd get all of that again. These will then generate these template items. The template items is generally the harder part, but then from here you're going to do a common denominator here. You won't multiply the common denominator by mixing things up, but you will keep them in a product format and do everything here in terms of the fraction algebra. X plus 1 goes in there, x plus 3 times, you'll have a times x plus 3 plus this goes in that, x plus 1 times and multiply with that, right? All of this here will equal this in terms of the computations of those linear equations which will develop. Open up that numerator. You have ax plus 3a plus bx plus b is equal to 2x plus 3. Now look for your linear variable items. You have ax, bx and 2x. Then the constants are these, right? Take these separate systems and look at only their coefficients and write them out. You have ax, bx and 2. That's an a plus b is equal to 2. Then you have a 3a plus b equals 3. You might as well say you have 3a plus b is equal to 3, right? You do elimination here. When you eliminate it, what do you get? B's cancel out. You have a minus 2a is equal to minus 1. A is equal to 1 over 2. If a is equal to 1 over 2, what does that make b? Makes b 3 over 2, doesn't it, right? So when you end up doing this, what do you end up getting in terms of your this right here? Your decomposed partial fraction will become, in a you'll put 1 over 2, you'll have 1 over 2 into x plus 1, right? And then you'll have b as 3 over 2, which will be 3 over 2 into x plus 3 dx. That right there is the decomposed partial fractions, which can be much more easily integrated. When you integrate this, you look at everything here with the coefficients pushed out and you have simple expressions come out from there, and it's not hard by any means. You know the natural logs are going to come out over here. You'll have 1 over 2 natural log x plus 1 plus 3 over 2 natural log x plus 3. If you want, you can combine everything here under a common denominator of 2. You can, I won't, but this right here is your final answer and it will be right. The second and last question is actually quite interesting. When you look at it, it looks interesting. It would be difficult to integrate this, but when you do the partial fraction decomposition, it will become easy. We have to analyze this. When you open it up in the denominator in terms of the factors, you have this 1 minus x squared develop. But if I look at that numerator and I look at the denominator, what can I do? Eventually, what can I do? I have 1 minus x here and I have 1 plus x. I can multiply this numerator by a minus, and I can flip one of these numerator items and cancel it with one of these denominator items and make everything even more simplified. You see, this will cancel out with that. I'll end up having minus 1 over x cubed over 1 plus x. That's what I'll get. Now look, we have to analyze this. When we're looking at it in terms of all the factors, we have x times x times x times 1 plus x. I'm just avoiding placing all of these. But what do we get here in terms of our factors? We'll have 1, 2, 3, 4 factors. Why will we have 4? Because you have to look at all the combinations which arise from here. You have a over x plus b over x squared plus c over x cubed. You have a combination of an x squared and x cubed, right? Plus d over 1 plus x. That's everything which arises right there. So you have 4 factors in terms of these template items, 4 of these. Now I will erase some of this. You've seen all of this come into play, right? All of this, nothing over here was too out of the ordinary. I utilized that minus 1 and I cancelled everything out. This right here will be our template into which all the a, b, c and d values will go in, so we won't erase this because we'll need this. Anyhow, you have to do a common denominator. What can it be? It can be x cubed times 1 plus x. That's what it will be. X goes in this. Well, it goes x squared times 1 plus x times. B goes in it how many times? Well, it goes x times 1 plus x times. c goes in it 1 plus x times, right? And d goes in it x cubed times. You have to open all of this up. You have ax square plus ax cube plus bx square plus cx plus dx cube. All of this is going to equal to what? Well, it's not going to equal to x minus 1. If you remember correctly, I eliminated some factors over here. The x minus 1 with the minus, I flipped it out and it became 1 minus x. In the end, my numerator was nothing more than just a minus 1. It will equal a minus 1 only. But I could put in all of these placeholders, 0x cubed plus 0x squared plus 0x minus 1. That's what it will really equal. So don't make this mistake here. Remember, when I factored this out, I had 1 and then I had a 1 minus x. Then here in the denominator, I had a x cubed into 1 minus x squared, right? But this 1 minus x squared was really a 1 minus x times 1 plus x. When I cancel this out, I was left with minus 1 over x cubed over 1 plus x, which has generated all of this. This right here became my new numerator, which right here you're seeing in terms of minus 1. Anyhow, we've re-clarified it. Now you have to look at all the systems which develop here. Look at the cube components. You have ax cubed plus dx cubed, which is a plus d is equal to a 0. Another system in terms of the squares are ax squared plus bx squared is equal to 0. You have a plus b equals 0. Another in terms of these linear variables, the single exponent variables are b plus c, right? B plus c is equal to 0. And then lastly, you have a c, a constant here, which is equal to minus 1. When you do this, everything falls into play. If this is equal to minus 1, based on this equation, b must be equal to 1, right? b is equal to 1. If b is equal to 1, based on this expression here, a is equal to minus 1. If a is equal to minus 1, based on this, d must be equal to 1. We can put our answers like this: minus 1, 1, minus 1, 1. Right here is what we have. And what we can do is here in each of these places, we can plug in those values, because then this right here will be what we will integrate through to completion, and then we will be done with this video. A was a minus 1, we'll leave it as that. B was a positive 1, C was a minus 1, and D was a 1. You just have to integrate that, and I'm going to create the space for you right over here. Anyhow, we have this minus 1 over x plus 1 over x squared minus 1 over x cubed plus 1 over x plus 1 dx. You could separate these in separate integrals I want, because I'll just do them like this. When I'm looking at minus 1 over x, I know it'll be minus natural log x, because if I were doing it separately, this is what would come out of it. When you're looking at this, you're doing a 1 over x squared dx, which is really a x to the minus 2 dx, and then you do n plus 1 over n plus 1, right? You'll have x to the minus 2 plus 1 over minus 2 plus 1. You'll have x to the minus 1 over minus 1, which is minus 1 over x, right? Minus 1 over x. From here, you're getting a minus 1 over x. Okay, that part is done. Now we look at the x cube. This minus integral 1 over x cube dx is same thing as minus integral x to the minus 3 dx. You're doing n plus 1 over n plus 1. Minus 3 plus 1 over minus 3 plus 1. We have a minus sitting out. You have here minus into x to the minus 2 over 2, which if you open it up, this should be a minus 2. You'll have a 1 over 2x squared. Alright? 1 over 2x squared. It's a little sloppy over here, but you can verify it on your side. Here you'll have 1 over 2x squared, but positive. And then lastly here you'll get natural log x plus 1 plus c. Let's clean everything up here and rewrite our good answer here with proper order. Our final antiderivative is natural log x plus 1 minus natural log x plus 1 over 2x squared minus 1 over x plus c. This here is the antiderivative of that rational function, handled by means of partial fractions decomposition, and it should be right. Everything here you've seen is not overly hard, but you've seen it and you can see how the procedures are. Thank you for watching. Have a nice day.